All right. Good morning, everyone. We are in the end game now. Okay, so here's what we're going to do today. First, I'm going to just go over one more fact about Bessel functions that is worth knowing, worth keeping in mind. Then we're going to spend the rest of today and Wednesday talking about orthogonal functions from a somewhat more abstract perspective, a little bit of a step back. The goal is, even though we're not going to have time to cover that chapter of the book that is titled Quantum Operators, I want to give you enough background so that you could on your own read that chapter. It's not essential for quantum mechanics, in that your quantum professor next fall will no doubt cover these things on her own. But if you were to read that chapter sometime between now and next fall, it wouldn't be a bad thing. It would help you if you want to get a head start on quantum mechanics. And so I want to give you some of the ideas behind that. But the first thing I want to do is I want to talk about another way of representing Bessel functions. We've been talking about Bessel functions as solutions to the Bessel differential equation. But we could also write Bessel functions in terms of integrals. And I basically made that assertion a few weeks ago when I talked about the Fourier transform of a circular aperture. And I said that if we were to take that Fourier transform from r equals 0 to r equals the a, that's the usual terminology for the radius of a circle in optics, and from phi equals 0 to phi equals 2 pi of e to the I kr cosine of phi r dr d phi, I made the assertion that the integral over phi is J0. I asserted that J0 of kr is the integral from 0 to 2 pi e to the I kr cosine phi d phi. And more general, Jm of kr turns out to be the integral from 0 to 2 pi of e to the I m phi e to the I kr cosine phi d phi. Now, there's a few ways that we could show this. One way we could show it is that we could try to write down a Taylor series for that integral. And maybe thinking, okay, wait, write down a Taylor series of an integral. Well, we're taking derivatives of an integral, but doesn't integration undo differentiation and vice versa? The integrals over phi, we would be taking derivatives with respect to this variable, which I'll just call x. That would be one way to do it. Another way to do it would be to show that it satisfies the same differential equation. Because if it satisfies the same differential equation as Jm, then, well, there's only two things that satisfy that differential equation: the Bessel function of the first kind, Jm, and the Bessel function of the second kind, Ym. But Ym doesn't blow up, sorry, Jm doesn't blow up, Ym does. So then we could look at this integral and we could ask, okay, what happens when x equals 0? And even before we show that it's Jm, we can immediately rule out Ym, because if I plug in x equals 0 here, you tell me, if I plug in x equals 0, does this integral behave nicely? Our integral just becomes the integral from 0 to 2 pi of e to the I m phi d phi. And last I checked, that integral behaves nicely. That integral doesn't blow up. So if it's not ym, and it obeys the same differential equation as jm, then it's got to be jm. Now we just need to show that it obeys the equation. I'm just going to do it for J0, all right? Because Jm, it's a little bit messier, but the same basic techniques apply. All right, so remember the differential equation is d squared j dx squared plus 1 over x dj dx plus 1 minus m squared over x squared j equals 0. Or if we take into account the fact that m equals 0, this whole thing becomes a lot easier. So let's take those derivatives, all right? D by dx of the integral from 0 to 2 pi e to the I x cosine phi d phi. Well, that is going to be, let's see here. We're taking the derivative of an integral. Now, we're not differentiating with respect to the variable that we're integrating over. And we're not differentiating with respect to a variable that's in either of the endpoints. We're just differentiating with respect to something up there. So that becomes the integral of I cosine phi e to the I x cosine phi d phi. And then the second derivative of all of that integral, that whole thing, is just going to be minus the integral of cos squared phi e to the I x cosine of phi d phi.
Professor?
Yeah.
So you use second order differential equation to check what?
I want to see if this thing is in fact a Bessel function. I've been asserting that this integral is a Bessel function.
Okay.
I'll prove it.
Okay, got it.
Little known fact about science, we tend to prove our assertions unless the algebra is really tedious, in which case we refer you to a book. But all jokes aside, even when we refer you to a book, we're referencing literature that has evidence in it. Okay. So what we get is that the integral, if I were to add these things up, well, I have almost the same integrand each time. So I'm just going to put everything inside. I'm adding up 3 integrals, so I'm just going to put them all inside. I'm going to get minus cosine squared phi plus I cosine phi plus 1 e to the I x cosine phi d phi. And the question is this 0? Because it better be if it satisfies the Bessel equation, but it's not at all obvious that it satisfies the Bessel equation. All right, it's not at all obvious that this is 0, that if I integrate this thing with these 3 terms in it, I get 0. We have to show that we get 0. One thing I can do is I can combine these two and I get sine squared phi. 1 minus cosine squared phi is just sine squared phi. Oh, and I should have been dividing by x. My bad. I should have divided the middle term by x. So then our question is, do we get 0 when we integrate sine squared phi plus I over x cosine phi e to the I x cosine of phi d phi? Well, sine is the derivative of cosine. So I'm going to do some integration by parts. I'm going to take this first part here, and I write that as minus I sine phi, oops, not plus, times I sine phi e to the I x cosine phi d phi. Because, and I will then write this furthermore as minus I sine phi times x over x. I'm allowed to multiply by 1. The reason I'm doing that is because the derivative of this thing up here is minus I x sine phi. It's derivative with respect to phi. All right. So I've got the integral from 0 to 2 pi I sine phi over x times minus I x sine phi e to the I x cosine phi d phi. Now this is all a very elaborate buildup to integrating by parts. This we call u. This we call dv. If we call this thing dv, that's the derivative of e to the I x cosine phi. And then u, well, let's see here. du should be the derivative of this thing, I cosine phi over x d phi. So we've just done a bunch of messy integration by parts. And I'm doing this for two reasons. One, of course, is that we need to establish the facts behind our assertions. And if messy integration by parts is one of the steps leading up to it, so be it. The other is that we're going to need to use messy integration by parts. I have no idea why that pop-up keeps showing. We're going to have to use messy integration by parts a few times this week. So now we can do our integration by parts. We're going to get uv evaluated from 0 to 2 pi minus the integral of v du from 0 to 2 pi. Well, uv, let's see, that's going to be I sine phi over x e to the I x cosine of phi 0 to 2 pi minus the integral of I cosine phi over x Any questions on the algebra leading there before we start evaluating terms and hopefully canceling some things? Going once, going twice. Anyone? Anyone? Okay. Now let's see, we're evaluating this whole thing at 0 and 2 pi. What's the sign of 0?
0.
And what's the sine of 2 pi?
0.
That goes away. So we're just left with this. Now, we could try to make sense of this integral. But remember, this integral here is what we got when we took the first part of this integral up here. And the second part of the integral is this, which is minus what we have below. So it looks to me like this and this cancel. So indeed, all of the things that we get when we plug this integral into the Bessel equation, they may not look like they cancel because the integrand itself is not 0. There's no guarantee that I cosine phi over x minus cosine squared phi, that all plus 1, that all of that will add to 0. They usually don't. But we don't need the integrand to be 0. We just need the integral to be 0. And so if we plug this integral into Bessel's differential equation, we get something messy out, and then we integrate it. What we get is indeed 0. Therefore, integral from 0 to 2 pi e to the I x cosine phi d phi 1 satisfies the Bessel equation with m equals 0, and 2 doesn't blow up. The first fact means that it could either be Jm, Ym, or some combination of those. The second fact rules out anything involving Ym, so the only thing it could possibly be is Jm. Any questions? Now at this point you could ask, okay, what if m is non-zero? If m is non-zero, we get the same type of algebraic gymnastics. We just have something slightly more complicated each time we take a derivative with respect to x. Actually, no, we don't get anything more complicated when we take a derivative with respect to x, but we get something a little bit more complicated when we integrate by parts. And that thing that's more complicated when we integrate by parts gets canceled out by some factors of m squared that show up from the Bessel equation. So it would be the same gymnastics, just slightly messier. Another question you could ask is, why do we care beyond the fact that Dr. Small made an assertion a few weeks ago and now he's trying to be scrupulous? Well, we care because a lot of the time these functions show up in the context of diffraction theory. You write down some diffraction problem, you say, all right, I've got an aperture that's circular and I want to integrate over it. And we need to show that when you set that integral up, you get the thing that you get actually is the Bessel function. Or if somebody set up a slightly more complicated integral for a little bit of a more complicated aperture, that what they would get would be, instead of J0, maybe J1 or J2 or whatever. So that's the other reason why we want to do this. A final question you could ask is, are there integral representations for the other Bessel functions? Bessel function of the second kind, Ym, or the Hankel function, or the modified Bessel functions. There are integral representations for the entire zoo of special functions. We could have a David Attenborough come in there and say, and now we consider this subspecies of Bessel function, which is often represented by the integral of yada yada. Yeah, we could come up with integrals for all of those. This is the one that shows up the most often when you're doing something very practical, like trying to find the diffraction pattern of a circular ring. And people care about diffraction patterns of circular rings because circular optical instruments are built up of many different rings, and complicated phase masks are built up of many different rings. Any questions? Then let's go back to an idea that we've been using periodically throughout the semester, which is that functions.
Professor, I'm so sorry. Do you mind? Just
Go
my
ahead.
curiosity's itching. Do optical fibers fall into the category of Bessel functions? Or is that completely separate?
An optical fiber is not literally a Bessel function.
Well,
The wave inside the fiber is represented by a Bessel function. Absolutely.
okay.
That last week, yeah.
So it's not the, because in my head you said the diffraction of light, and so when I'm thinking of an optical cable, I'm thinking of total internal reflection. So I was just curious if there was some sort of divergence there.
No, light can do more than one thing. And so you use Bessel functions to describe waves in cylindrical geometry. And you can have a wave that's spreading out in cylindrical geometry, in which case your diffraction pattern is a Bessel function of angle, telling you how much light is present at each angle.
Mm-hmm.
You can have light that's confined in a circular geometry, in which case your Bessel function, your wave is a Bessel function, and the input to that function is the distance from the center of the fiber. So when you're describing a wave in a cylindrical geometry, it is likely that a Bessel function will show up in there somewhere.
Okay.
Whether it's a confined wave or a spreading wave. If it has a circular pattern to it, somewhere in there, there's probably a Bessel function.
Okay. Okay, cool.
And you shouldn't worry too much about the fact that, wait, in this one case, the light was confined, and in another case, it's spreading. We use complex exponentials, sinusoidal functions to describe waves in all sorts of situations. Oftentimes, it's the way that you combine those waves that either makes them spread or stay focused. But either way, it's a combination of a bunch of complex exponentials. Now, I've been saying that functions are vectors. And by vectors, we don't mean in the three-dimensional geometry sense of something with x, y, and z coordinates and the length and the direction. We don't literally mean an arrow in 3 dimensions. What we mean is that they are elements of a vector space, elements of a space of vectors defined in a more general abstract sense. And if you think that using the word vector in 2 ways is kind of counterintuitive, you should take a class on abstract algebra, where they have things that they call groups, which are only similar to the normal meaning of the word group in that there's more than one thing in the group. They've got things called rings, which have nothing to do with rings. They don't even have anything to do with hobbits and dark lords, yet somehow they are called rings. They've got things called fields, which are not like, planes of grass, nor are they like an area of study, except that, well, you could study rings, nor are they like the fields of, gravitational fields or electric fields or magnetic fields. This is like the least objectionable term you will find in abstract algebra. And the vector space has 2 operations. It has addition of vectors, and this addition is commutative and associative. Basically, it doesn't matter what order we do our addition in. We have multiplication by scalars, and those scalars have to obey a few properties that we're not going to worry too much about, except to say that the real numbers and the complex numbers both satisfy those properties. Real or complex numbers for our purposes, but there are plenty of other types of scalars. And those scalars are what the mathematicians call, are elements of what the mathematicians call a field. And that is distributive and commutative. We have a zero vector. That's just a vector that if you add it to anything else, will give you back the same vector. We have a unit scalar. And each vector has an additive inverse. What do these things mean? That just means that f plus 0 equals f. F times 1 equals f. And f plus negative f equals 0. It seems so trivial that you're wondering why I waste time on it, but if you go look very carefully at whatever book you used for linear algebra, most of the important facts of vector spaces were derived from these axioms. They didn't spend a whole lot of time dwelling on the fact that, well, these vectors are four-dimensional column vectors or whatever. They didn't spend a whole lot of time dwelling on x, y, z coordinates. Most of the important theorems of vector spaces could be derived from a few simple axioms like this. And well, if I've got a set of functions of say one variable x, or three variables x, y, and z, or four variables x, y, z, and t, if we're solving a wave equation in three spatial dimensions and one time dimension, or a function of many more variables if we're doing quantum mechanics of several interacting particles, all of these functions that we could think of satisfy these properties. Now there's a sixth property that's pretty important. We have an inner product which we have usually been defining in particular, but I'm going to write it very generally. The integral from a to b, and exactly what you choose for a and b will determine whether any of these theorems apply. Of f star of x, g of x, rho of x, dx. And rho is something we haven't said much about yet. Rho is something that we haven't used, but it showed up indirectly, it showed up sneakily. Rho is a weight function. Right? It's real. And non-negative between A and B. All right.
So is that what mathematicians refer to as weights? Objects that are real and non-negative?
No, it's a weight. The weight function, think about it like a weighted grade. Okay, you say, all right, well, your midterm counts for 15% and your homework counts for 20% and the next midterm counts for another 15%. It's how much to multiply each thing by when adding them up. Okay, so like if each midterm counts for, and I forget exactly what the formula is in here because you've got so many things on that list. But each assignment is a certain percentage of your grade. So you take the grade on this assignment and you multiply it by whatever percentage, a weight. Then you add to it the grade on the next assignment, multiplied by whatever percentage, a weight. All right, well, this is just a generalization of that. We're taking the product of f star g at one value of x, multiply it by a weight. Then we add multiply by dx. Then we take the product of f star g at another value of x, multiply it by another weight, multiply by dx. Then add to that, again, the product of f star g multiplied by another weight, multiplied by another dx. Okay, it's just like calculating a weighted grade. Now, we mostly said that rho of x is 0, except when we didn't. Because remember, for Legendre polynomials, we talked about how you could compute PL of x, PL prime of x dx. And we said that this is 0 if L is not equal to L prime. And then it was like 2 over 2L plus 1 if L equals L prime. So in this case, rho of x is 1. But we also would change variables. X equals cosine of theta. Then dx would be minus sine theta d theta. And then we would swap our, and I should be even more careful. Rho equals 1, A equals minus 1, B equals plus 1. Then we would integrate from A equals pi, or 180 degrees, to B equals 0 in any set of angular units. And you're thinking, no, we don't integrate from pi to 0. We integrate from 0 to pi. But you see that minus sign there? That minus sign flips the limits of integration. So we would do integral from 0 to pi of PL of cosine theta, PL prime of cosine theta, sine theta, d theta. Right? Or we might flip them around. Yeah, we would actually have to flip around. B equals pi, because rho is supposed to be non-negative. This is rho of theta. And you could say, well, wait. The weight function has to be non-negative. But sine theta is negative. Sine theta can be negative. Well, the requirement is that it's non-negative between A and B. And sine theta is non-negative between 0 and 180, or 0 and pi. So this was an example of a weight function. We also saw weight functions for Bessel functions. We have the integral from 0 to r of Jm of k r over alpha mn, Jm of k r over alpha mn prime big R. Wait, that shouldn't be, there shouldn't be a k there. It should just be R over, whoa. Created a whole lot of alpha mn R over big R, Jm of alpha mn prime R over big R, R, where alpha mn and alpha mn prime are zeros of Jm. So if little r equals big R, then our input to this Bessel function is 1 times alpha, whichever alpha it may be. Okay? And here R is our rho. Rho of R equals R. Notice another thing, which is that We chose our range very carefully so that our Bessel functions were 0 at the end of the range, right? So when we get to the upper limit, our Bessel functions are 0. And at the lower limit, our integrand is 0, because even though there's no guarantee that Jm of 0 is 0, this thing is 0. At our lower bound. And that's something that we just kind of worked out piecemeal last week. We just played around with things and we saw that certain integrals worked out. It's just a fact that worked out. Well, now I want to show you that selecting our limits very carefully is part of a bigger theory. It's part of a bigger framework. Any questions? Okay, if functions are vectors, vectors have lengths, so do functions. And they often denote the length of a function with 2 of these absolute value signs. And the reason why they denote it that way is that there's a difference between the absolute value of a function at a particular point versus the length of a function as a vector. Because if I've got some Bessel function and let's say that I've got a Bessel function that looks like this, okay? Now let's say that down here it's negative 0.2. Whatever, all right? F equals negative 0.2. Absolute value of F equals plus 0.2. But the length of F is equal to the integral from 0 to R of absolute value of F squared R dr, okay? And strictly speaking, that's the squared length. So they use the double absolute value sign to denote the length of a function as a vector, and the single absolute value sign to denote the absolute value at one point. If all I want to know is the absolute value at this point, I just plug in that value of x, take the absolute value, whatever that number is, that's the absolute value of the function at that point. If I want the length of a function, that's an integral. Any questions? Well, when we spoke of vector spaces, finite dimensional vector spaces, we had linear operators, and we can represent linear operators with matrices because we can represent the vectors with column vectors. We could represent the elements of the vector space with column vectors. And so you've got a matrix acting on a column vector, and that equals a new column vector. All right. Well, for functions, functions are elements of infinite dimensional vector spaces. I can't really write down a function with a column vector very easily. I could approximate a function with a column vector. I could approximate a function with a finite number of elements. I could say, all right, this actual function is very complicated, but I'm going to write this function maybe as a Fourier series, and I'm only going to look at the first few terms because I get a very accurate approximation. I don't get the exact value, but I get an accurate approximation from the first few terms. Or I'm going to write this as a series of Legendre polynomials. And of course, unless I write down an infinite number of Legendre polynomials, I won't get the function exactly, but maybe the first 3 Legendre polynomials are accurate enough. Maybe the first 4 or whatever. And then last week we talked about how we could represent functions with Bessel functions. And again, in practice, in principle, I would need an infinite number of Bessel functions, but maybe I'd only need a handful of Bessel functions to represent something accurately. But because a function is really an element, the ordinary functions we usually work with are elements of infinite dimensional vector spaces. We can't necessarily write things down in this way, but we can write things down naturally. We can write down some very simple linear operators. I'm going to give you the 2 linear operators you're going to work with the most in quantum mechanics. And one of them is so simple you don't even think of it as an operator. Multiplication by a function. U of x, psi of x is a linear operation on psi. U is some function. U could just be x. U could be 1 over x if it's the potential energy of a hydrogen atom. It could be x squared if it's the potential energy of a harmonic oscillator. It could be some sinusoidal function. It could be a periodic function. Those are important in crystals. It could be all sorts of things. But this is a linear operator because U of x times psi 1 of x plus psi, or a psi 1 of x plus b psi 2 of x equals U of x times a psi 1 of x plus U of x times b psi 2 of x, all right? That's linear, meaning that if I have this operator acting on a linear combination of vectors, I get a linear combination of U of x times each vector. It looks trivial. You're thinking, why am I belaboring it? I'm belaboring it because everything that we ever talked about with matrices, like matrices having eigenvalues, matrices having eigenvectors, matrices being Hermitian so that the order in which you take certain inner products doesn't matter. All of those properties apply to linear operators. Yes, even the really, really easy ones, the ones so simple that you think that there must be a trick, that someone must be fooling you. Here's another linear operator. Derivative. D by dx of a psi 1 of x plus b psi 2 of x equals a d psi 1 dx plus b d psi 2 dx. That's a linear operator, right? Because whether you first take the linear combination and then act with the derivative operator, or first take derivatives and then take derivatives of the individual pieces and then add up linear combinations of the pieces, you get the same thing, right? So the derivative is a linear operator. Something a little bit less obvious. which is that u of x and minus I d by dx are Hermitian operators. Now you're wondering why minus I? I'll get to that, because if we don't put in the minus I, weird things happen. The minus I makes everything right, and I'm going to show you. Okay, what is a Hermitian operator? We're used to Hermitian matrices. The matrix is Hermitian. Well, what that means is that if we have the two vectors, v1, v2, what that means is that v1 hv2 equals hv1 v2. So if we first had the matrix act on the vector v2 and then take the inner product with v1, that would be the same as having the matrix act on v1 and then take the inner product with v2. Right? That's what that means for matrices. You could multiply the matrix by this vector, then take the inner product with that vector. It'd be the same as having the matrix operate on this vector, then take the inner product with that vector. Well, for functions, it's not at all obvious, because naively we might think, okay, f times minus I dg dx is in general. Sometimes there are exceptions, but usually that's not the same. Or even I should be writing this as f star. That's not the same as g star, or it's not the same as g times minus I df star dx, okay? These two things are different. So you're thinking, okay, if these two things are different, if taking the derivative of one function and multiplying the other is not the same as doing the derivatives in the reverse order, then how can I say that the matrix element, that this operator is Hermitian? Remember, hermiticity is a property of inner products. So the question I should be asking is this: is the integral from a to b of f star of x times minus I dg dx dx, is that equal to the integral from a to b? And I should really be writing it like that. You'll see why. It's not equal to the same. Is that equal to, I'll write it like this. Okay, now let's just start talking about why we did these things, why we did the complex conjugates the way that we did. Fg is the integral of f star g dx with rho equals 1. Fg is that. F dg dx is the integral of f, there should be a minus I there, f times minus I dg dx. Now, what if I had minus I times the derivative of f, all right? I could have minus I df dx inner product with g. Oh, and I left out the complex conjugate. The rule is that the first thing gets conjugated in the integral. All right. So if I take minus I df dx, and then I take its inner product with g, and I put this whole derivative in the first position of the inner product, whole thing complex conjugate g dx. That is, if I then complex conjugate it, a b I df star dxg. You're thinking, well, what if I'd done things the other way? What if I had g minus I df dx? That would be the integral from a to b of g star times minus I df dx multiplied by dx. And the whole idea is that I should be able to have, if this operator is Hermitian, if this operator is Hermitian, then I could have it act on either function, take the inner product, and as long as I follow the rules of order in an inner product, as long as I say that whatever thing I put into the first position gets complex conjugated, and whatever thing goes into the second position doesn't get complex conjugated, then I should get the same result. So our basic question is, integral from a to b, I d by dx f star g dx, is that equal to the integral from a to b of f star times minus I dg dx? That's the question we need to pose. That's the thing that we need to try to prove that those two sides are equal. Because if those two sides are equal, then that means that the operator is Hermitian. And you're thinking, why do I care if the operator is Hermitian? Because if the operator is Hermitian, then it has orthogonal eigenfunctions. It has real eigenvalues, right? That's what we're trying to prove. Any questions? Any questions? Well, we're going to use our favorite tool. We're going to use integration by parts. I'm going to work on this side. I'm going to call this u. I'm going to call this dv. So then du is df star dx times dx, and v is equal to g, and the minus I is just a constant, right? So this whole thing becomes minus I times f star g evaluated at a and b, minus, because there's always a minus sign when we integrate by parts, this minus I is the constant from the beginning, integral from a to b of v du, or g df star dx dx. Minus minus I becomes plus I. And so then our basic question is, can we say, well, this whole thing turns into minus I f star g evaluated at the endpoints plus I integral from a to b g f star, sorry, g df star dx dx. Here's the thing that we wanted to try to make equal to it. Here's the thing on the other side. This is our problem. Must insist f star g equals 0 at the endpoints. So everything that we're doing here is only valid if we limit ourselves to a set of functions that are 0 at the endpoints. So minus I df d by dx is Hermitian if it acts on functions that are either 1, zero at the endpoints, 2, same at the endpoints, i.e. periodic. And that's, you're thinking, well, that sure limits us. Well, to a mathematician, that limits us, because to a mathematician, the universe has an infinity of functions. And we've just ruled out a whole bunch of them by only considering the ones that are 0 at the endpoints. But let's think about what we care about a lot of the time in physics. We tend to either care about waves who have finite integral, oftentimes we want that, the length of the vector, to be finite. Thinking, well, what does it mean to say that the length of a function is finite? Well, the energy in an EM wave or an EM field is the integral from minus infinity to infinity of 1/2 e squared plus b squared dx. If that integral is finite, then E and B must go to 0 at plus or minus infinity. All right, that's the only way that any of this is going to work. So we must be talking about EM fields that go to 0 at infinity. We often limit ourselves to fields like that in physics, or functions like that in physics. Likewise, if you're taking 2540 or you've taken 2540, by now you've probably learned that the probability density in quantum mechanics is the absolute value of psi squared. Therefore, the integral from minus infinity to infinity So psi has to go to 0 at plus or minus infinity. We often deal with functions like that. Maybe you've dealt with the particle in a box in quantum mechanics. Here are the ends of the box, x equals 0, x equals L, and all of the wave functions looked like that, or like that, and so forth. All right, well, that would also be particle in the box wave functions are 0 at the endpoints. Periodic functions, waves in a crystal, waves in some repeating system. Now there's a little bit of a nuance on there, but we're not going to worry about that today. Maybe I'll talk about Bloch's theorem and some of the subtleties there some other time. But in general, in physics, we deal with periodic functions a lot. So as long as we deal with periodic functions, then we're okay. So I've just shown you 3 classes of functions that show up a lot in physics. Functions that go to 0 at plus or minus infinity, so that the total amount of energy stored in this field or the total amount of probability stored in this wave function is finite. Functions that go to 0 at the edges of a system, whether it's a quantum particle in a box, or let's say an electromagnetic wave inside of a metal box. And you might have used an electromagnetic wave inside of a metal box to heat up your breakfast this morning. A microwave oven is just a metal box that has an electromagnetic wave in it, and the field goes to 0 at the surfaces of the conductor. That's a very practical field used all the time in physics. People use microwaves in physics for more than just warming up their lunch in the lab. But the point is that people routinely build devices where an electromagnetic field is confined to a finite region of space. So, all right, I think I've established that we've got a class of functions for which this works. Then in the interest of time, I'm just going to say that since Hermitian operators exist and show up in differential equations, notice how I just proved that the 2 things that show up in all those differential equations we've been working with, that those things are Hermitian. Because think about all the differential equations you've dealt with for the past few weeks. You take some derivatives, and maybe you've got 1 over x times a derivative. Well, 1 over x is a function of x. 1 over x is a Hermitian operator, okay? X squared is a Hermitian operator. And in the Bessel equation, we get 1 over x or x squared, depending, multiplying, or 1 over x squared. We get all of those things depending on how we write out functions. In the Legendre equation, we've got 1 minus x squared multiplied by something. 1 minus x squared is a Hermitian operator, okay? The derivative is a Hermitian operator. All of these things that show up in our differential equations are Hermitian operators, okay? So all of the differential equations we've studied for the past few weeks have Hermitian operators in them. They have real eigenvalues and orthogonal eigenfunctions. And that, I'm not going to repeat the proof that we did a few weeks ago when we were dealing with linear algebra and finite dimensional vector spaces, but it just goes down to, you've got a linear operator, L operating on some function yi equals lambda I yi, possibly times a weight function, right? And then you take yj star and that becomes y I integral, when you take the inner product, integral from a to b of yi yj star lambda I rho of x dx, and then you do it in the other order. Instead of having the linear operator act on yi, you have it act on yj, and you get back basically the same integral with a different prefactor. And so you prove that the eigenfunctions are orthogonal. And then you do it with the same thing with I equals j, but depending on whether you have it act on either yi or yi conjugate, you wind up getting either lambda or lambda conjugate, but lambda and lambda conjugate have to be the same. So we get real eigenvalues. Here's the key thing. We have differential equations that could be written in the following form. P of x d squared y dx squared plus dp dx dy dx plus q of x times y equals minus lambda, I'll write as plus lambda, rho of x times y. All right, that's how we have been writing a lot of these differential equations. It may not always be obvious that they are that way. Sometimes it is. If you've got 1 minus, we can rewrite all of this as d by dx of p of x dy dx plus q of x y equals lambda rho y. This is a Hermitian operator acting on y. Now, one thing you're thinking is, wait, I see derivatives. But Dr. Small told us that I times a derivative is Hermitian. Yes, I times a derivative is Hermitian. But if I were to put an I here and an I there, I would just get a -1. And I could absorb that -1 into the definition of P. You know, if P were minus 2x, I could replace P with 2x or vice versa, right? So I've got a Hermitian operator acting on this y. Hermitian operator acting on y equals lambda rho y. Therefore, 1, lambda is real, and 2, integral from a to b yi of x y star j of x rho of x dx equals 0 if I is not j. We've been proving that over and over again. Selecting particular forms, we take a certain differential equation, and I would do some manipulations on that differential equation, say, hey, I could write it this way. And then we would get out that, hey, if I write it this way, I evaluate at these endpoints, and I get this eigenvalue, and then we write it a slightly different way, and we reverse some labels, and we get out the same endpoints, and we get the same integral multiplied by a different eigenvalue. And I say, hey, same integral, different eigenvalue, the integral must be 0. Well, now I'm just asserting it from a theorem, okay? I'm saying that it comes from the same place that all of these things in linear algebra come from. Let's play with a few of these functions in the last 6 minutes. Legendre. The Legendre function was 1 minus x squared d squared y dx squared minus 2x dy dx. Sure enough, this is d by dx of 1 minus x squared equals minus L times L plus 1 y. So that's lambda. And then rho must just be 1. Bessel. X squared d squared y dx squared plus x dy dx minus minus m squared y plus k squared x squared y equals 0. That doesn't look like this form. You might be saying, well, wait, that x multiplying the first derivative, isn't x the derivative of x squared? Not quite. 2x is the derivative of x squared. But I can manipulate it into that form if I simply divide both sides by x and move this to the other side. So if I have x d squared y by dx squared plus 1 times dy dx minus m squared y over x equals minus k squared y times x. This is p. P is just x. dp dx is 1. Q is minus m squared over x. Minus k squared is what we're calling lambda. And x is what we're calling rho. Any questions? Going once, going twice. Sometimes it's even less obvious that a function is like that, but with a little bit of work, you can make it like that. Here's something called the Laguerre equation. I'm deliberately doing one that we haven't worked with before to show that this technique works for problems you haven't yet solved. All right. This is not d by dx of x. Doesn't look like that. Doesn't look like we have it in that form, which is called, by the way, there's a name for this. This is called Sturm-Liouville form. Just named after two people who worked on this. This is not in Sturm-Liouville form. But let's multiply both sides by some unknown f of x. X f of x times the second derivative of y plus 1 minus x f of x times our first derivative of y equals minus nu times y. Minus nu will be our lambda. Y is our function. It's f. Whatever f might be, that'll be our rho. That'll be what we have to weight things by when we're taking inner products. So x f of x equals P of X, and 1 minus X f of X equals dP dx. Okay, now we have to find f. Well, we've got this differential equation here, but it has two unknown functions in it. Do you see any way that I could get rid of f in the second equation, maybe using the first equation? F is P of X over X using the first equation. So we get 1 minus X over X P of X equals dP dx. Or dP over P equals dx over X times 1 minus X. And if you solve for all of that, you get that P is X e to the minus X. And F is just e to the minus X. So we finally put it all together. We get that X e to the minus X d squared Y dx squared plus 1 minus X times e to the minus X dy dx equals minus nu Y e to the minus X. And so we could conclude that the integral from 0 to infinity of y I of X, y star j of X, e to the minus X dx equals 0 if I is not equal to j, which means that without even solving the differential equation, we just use these facts about the equation, use the fact that this is all a Hermitian operator, that this entire left side here is just d by dx of x e to the minus x dy dx, that this whole thing here is a Hermitian operator, to immediately figure out what property the eigenfunctions have to solve. And with that, we're a little bit over time. I'm going to pause here. On Wednesday, I'm going to talk about the Heisenberg uncertainty principle and prove it using what we've been discussing, and prove that it holds not just for quantum weirdness, but for all Fourier transforms. Have a good day.
Thank you, Dr. Small.
You're welcome.
Thank you, Dr. Small.
Dr. Small, do you mind if I just take a screenshot of those notes real quick?
I already disconnected, so what I'll do is I'll upload the PDF to Blackboard right now, like I've been doing every day all semester.
Okay, cool. Thank you, Dr. Small. See ya.
Bye.
I had a question, Dr. Small.
Sure.
We're just about the function spaces.
Uh-huh.
So for a given that like a function space has like infinite number of functions that you put in as like a input, right?
Mhm.
Are the eigenfunctions, are there also infinite amounts of those? Or
Yes. And it's an infinite dimensional function space. It's an infinite dimensional vector space. And since the eigenfunctions form a complete set, they basically form a basis for this vector space. Anything can be written out in terms of the eigenfunctions. They have to have, the set of eigenfunctions has to have the same dimensionality as the vector space itself.
right? Okay, thank you.
Mhm.
Hey, Dr. Small, I just needed help with question 1 on problem set 14. Like,
Okay,
I don't get how we're supposed to do the spreadsheet stuff. Like, are we supposed to, in Mathematica, do we put in Bessel J0? Or, because I tried that and I just got like some weird graph that I couldn't really make sense of.
so you should find the locations of the 0. So Bessel J0 is a function that will work in Mathematica. I'm not sure what it would be in Excel. But what I would do is I would go into Mathematica or Wolfram or wherever, and I get a list of Bessel functions, sorry, of zeros of the Bessel function. So the first 0 will be at 3.8, say, and the second 0 will be at, I don't know, 7 point whatever. And the third 0 will be at 10 point whatever. And I have a column of 1, 2, 3, 4, 5, 6, and a column of 3.8, 7 point whatever, 10
Right.
whatever. Just fill a line to that.
Okay. Oh, okay. And that, boom, I'm done. Like, that's what you were asking.
Okay,
Thank you.
you're welcome.